Yeah, this is our last week before spring break, so that's exciting. Get a week off next week. That's always good. I'm enjoying that. Well, we're going to go to Williamsburg, Virginia for 4 days, and then come back and move into our house. Finally moving in. So looking forward to that. It's only been since the beginning of the school year, basically September. We moved out in September, so we'll get that going. All right. Well, it's 8:05. Let's get going. Let's look at this week's cybersecurity. Blinky. Let's go to our grade screen. Okay, we are down to 5.03 network design principles. We had social engineering last week. Got a couple more lessons before the exam. Well, one more lesson. Well, the career connection. We'll see what lessons with that. I may play with those dates. I got to look at the last month to see what all we have to get finished before the end of the school year. So I may end up adjusting some of that. But you're a senior. You're going to have a shorter school year than the rest of us anyway. You're only going to be here a couple more weeks after the exam there. So you and Cade both are going to graduate on me there. But let's go look at 5.03. Network design principles. All right. Designing a network. So designing a secure network can be pretty overwhelming. Man, we've looked at all kinds of threats, and it'd be tough as someone in charge of that. Firewalls, routers, and switches contribute to the security of a network, but that's not always enough. Obviously, since we see these breaks, a network must be properly designed and configured to keep it running smoothly. Oh, we have a little video. So let's check out this little video on network security design principles.
Designing a structurally sound building is more than picking a style and choosing paint colors. A well-designed structure needs to have safety and stability from the foundation to the roof, and should consider the habits of the people who will actually use the space. Designing a network is a lot like designing a building, where established principles guide the choices made along the way. First, a secure network should be functional at all times. If equipment fails or conditions are overloaded, security should still be functional to protect valuable assets. Next, a well-designed system should always be secure, requiring an admin to turn security on or off. This failsafe prevents unauthorized users from tampering with the secure network and potentially risking exposure. To ensure that a network design is usable, security should be easy to access, meaning the system itself is user-friendly and simple to navigate. Finally, a secure network is adaptable. As a business grows, the network needs to grow with it. Security features should be expandable or updated to accommodate these changes. Solid design principles work in tandem to create a network that is fully protected.
That gives a little preview of what we're looking at this week. Let's go to page 2. Basic network design principles. So cybersecurity professionals have a big job when it comes to designing and creating a secure network. Luckily, they have a set of core principles to guide them in the right direction. These basic principles serve as a guide for proper and secure network design. So the core design principles include, as they said in the video, functionality at all times. Yeah, number one, your network needs to be up and running all the time because you generally got people working on it or need to be accessing it. The network should remain functional at all times, even in the event of failed links, equipment failure, and overloaded conditions. So you should have something running. The network should reliably deliver applications and provide reasonable response times. So you got to have some workarounds built in when something fails. The network should be secure, always, hopefully. It should protect the data transmitted over it and data stored on the devices that connect to it. Easy to troubleshoot. Yeah, troubleshooting should be as easy as you can make it. Finding and fixing the problem should not be too time consuming. And adaptable. The network should be easy to modify and adapt to network growth, because you're constantly going to be adding stuff to your network in any business, any organization. And so you got to be able to adapt and not have to break it down and rebuild it every time you change something in your network. Let's talk about functionality at all times. The network should always remain functional. So even in the event of failed links, equipment failure, and overloaded conditions, should be able to reliably deliver applications, provide reasonable response times. Fail-safe defaults. So the idea behind the principle of fail-safe defaults is that if a system fails, it should do so securely. Interesting. This principle requires the default access permissions to an object be set to none. The default access permissions set to none. So if it failed, the confidentiality and integrity of the system should remain even when availability is interrupted. So if something happens with the system fails, it shouldn't suddenly allow everyone to access all the information. So the default should be, or if something's failing, nobody can access it, right? Because you want to cut it off, because it may be hackers that caused it to fail, and you don't want that to open up all your information. During a failure, attackers must not be permitted to gain access rights to privileged objects that are not normally accessible. Upon failing, a system that reveals sensitive information about the failure to potential attackers could supply additional knowledge for creating a future attack. So a fail-safe default allows an administrator to determine what may occur when a system fails and be sure it does not threaten the system. So here's a real-life example right here. Notable credit card companies use advanced authentication technologies to prevent credit card fraud. Most notably, whenever someone makes a purchase in the store, the actual card is swiped through a device that calls the credit card company. You know, you got the little thing, you insert your card or you tap it or whatever, and it actually transmits something to the credit card company. Credit card company first checks to see, is the card stolen? Has it been reported stolen? Is this a valid card? Then the credit card company also analyzes the requested purchase in context of the cardholder's recent purchases and compares the patterns to overall spending trends. Like if I'm today, my credit card company gets a transaction that shows that I'm buying something in Portugal, it should compare that and goes, wait a minute, he was just in Northwest Arkansas yesterday. Portugal is nowhere close to there. This could be fraud. It should flag it right away. It should send me a message. Is this you? We've denied a transaction in Portugal. If that's you, let us know and try again. If their engine senses anything suspicious, the transaction should be denied. And I've had that happen where someone had stolen my credit card information, didn't have my card. I had the card, but I got a notification that like they were trying to use it at a McDonald's in Miami, Florida. Sitting in my living room, get a notice from my credit card company. Are you trying to use your card at a McDonald's? No, I'm not trying to use my card at Miami, Florida. So interesting. So it alerted me and they shut it down and sent me a new card. So always secure. So this is the second thing. The network should be secure. It should protect the data transmitted over it and the data stored on the devices that connect to it. Complete mediation. The principle of complete mediation requires that all accesses to objects be checked to ensure they are allowed. Objects being defined as physical devices, connected devices, and smart devices, buildings, other items embedded with electronics, software, sensors, actuators, and network connectivity. So objects is a lot of things. So first it determines if the user can read the object, right? Is this person authorized to access that? If so, then it provides the resources for the read to actually occur. But if the user tries to read the object again, the system again should check that the user can still read the object. You never know. It might be something that you get one-time access to it. And once you retrieve this, you're not allowed into it again. There could be some security reason for that. So it should check every time that the user tries to read the subject. Most systems would not make the second check. Instead, they would just cache the results of the first check and base the second upon the cache results. They'll just like, are they allowed to look at this? Yes. And it'll just save that yes. And any future requests, it'll just default. Oh, yeah, I've already checked. They said yes. Yeah, they can have it. Oh, yeah, they can have it. So that's most of the time it wouldn't do that. But there may be a need to do that. Sorry, you only have access once and then it's not again. So here's a real life example of that. An online banking or shopping website should require users to sign in again after a certain amount of time has elapsed. This prevents someone else from accessing the user's account on a shared or lost device. It's like at an ATM machine. Once you put your card in and punch in your code, it should time out right after that transaction. It should cancel, because if you walk away and it still has your account open, somebody else should just walk up and take another withdrawal. So that's one of those that it should make a check every time again, right? You should have to go through that, log in again every single time, just so somebody doesn't walk up behind you and take money. Separation of privilege. A system should grant access permissions based on more than one condition being satisfied, according to separation of privilege. This principle may be restrictive because it limits access to system entities. Before privilege is granted, at least 2 verifications should be performed. So let's look at a real life example and see what they're talking about here. For a user account to be verified, 2 conditions must be met. For example, the user must know the root password and the user must be in the right group. Or like I said with the ATM, you got to have the ATM card and the code. You know, multiple checks. The weakest link principle states the resiliency of software and devices against attacker attempts depends heavily on the protection of the weakest components. Could be the code, a service, or an interface. So yeah, that weakest link principle. What's the weakest part of your security? That's what you should focus on. Easy to troubleshoot. Troubleshooting should be easy. Finding and fixing the problem should not be too time consuming. So let's look at that concept. Economy of mechanism. One factor in evaluating the system security is its complexity. If the design, execution, or security mechanisms are highly complex, chances are good that security vulnerabilities increase. The more complex it is, the more chances there's something wrong or something conflicting or some hole you haven't noticed, some problem with your system. Simplifying design is not always easy, but it means when a possibility of security breach does occur, it's easier to understand and fix it. Yeah, the more complex it is, somebody's going to break in at some point. How quickly can you shut it down and lock them out again? Real life example. It's much easier to monitor user behavior and input if all users are forced into a few small channels. That's the idea behind having only a few entrances at sports stadiums, right? I mean, you put 80,000 people in the stadium, you think, gosh, I probably need about 40 doors so you can get in and out easily. But no, they limit it to like 8 or 10 doors. Too many entrances would make ticket collection more difficult, and more staff would be required to do the same quality job, and more security officers to make sure dangerous folks aren't bringing stuff into the stadium. So limiting to a few small channels. So that's good. That's a good example to think about sports stadiums as an example of that. Least common mechanism. In systems with multiple users, the mechanisms allowing resources to be shared by more than one user should be minimized as much as possible. This principle may also be restrictive because it limits the sharing of resources. If there's a need for more than one user to access some file or application, then these users should use separate credentials to access these resources. That helps prevent unforeseen consequences that cause security problems and lets you know exactly who all was in there as well. Real life example. Payroll is electronic in most businesses in the US these days. It used to be done with pen and paper, but now it's electronic. The salary a person is paid is private information, should never be shared with other employees. Causes lots of problems if everyone starts knowing what everyone else makes. So the least common mechanism is used to only allow payroll employees to access the servers that perform all the payroll tasks. This risk reduces the risk of other employees accessing the information they shouldn't be privy to. So sometimes even people that process the payroll may not have access to information about salaries and stuff. Just the information they need to know to process what they're getting paid this check. Like how many hours did they work? All right. Psychological acceptability. A security mechanism should not be overly complicated. Psychological acceptability recognizes the human element in computer security. So if security-related software or computer systems are too complicated to configure, maintain, or operate, the user will not fully employ the necessary security mechanisms. Oh man, I'm not going to go through all those steps. I'll just do this. Real life example. Your device might suggest a new password for a website or login, but it's overly long and complicated, forcing you to write it down on a sticky note, right? It has to be at least 14 characters. You got to have one special character. You have to have 3 numbers. You have to have 2 uppercase, 3 lowercase at least. You know, if it gets really, really complicated, no one's going to be able to remember it, and they'll put it on a sticky note. Oh, well, what good is that now? There's a sticky note that anyone can pick up and type in. This compromises security because the complicated password that couldn't be memorized is now posted for everyone to see. Open design. The security of a mechanism should not depend on the secrecy of its design or implementation. In other words, complexity does not add security. Open design applies not only to information like passwords or cryptographic systems, but to other computer-related security. Like a DVD drive and content scrambling system, known as the CSS protection, uses an algorithm to protect DVD movie discs from unauthorized copying. So if you buy a movie, you can't just throw it in a computer and make a copy of the DVD because it has this content scrambling system. All right. Let's look at page 6, probably our knowledge check. No, it's just all right. Adaptable. Oh, yeah, we haven't looked at adaptable. Leveraging existing components. When introducing new software or devices into the network environment, users should review the state and setting of the existing security controls in the environment, ensure they're being used by the new system. When you put the new system, is it being covered by the security system you have in place? Can you use the security system you have in place, or you have to add different security for this new component you're adding? Single point of failure. A single point of failure means if one part of the system fails, the entire system stops working. This can be extremely detrimental to an organization because the loss of revenue from downtime or any business is significant. Imagine if Amazon.com had a security failure that shut down their whole system. How much money do you think they make every minute that they're up and running? So a lot of lost revenue. Single points of failure should be identified and eliminated if possible. If this fails, it switches to this system. If that fails, it switches to this. You should have backup components in place so you don't run into that problem. Defense in depth. The idea behind defense in depth is to manage risk with a range of defense strategies. This strategy works because when one layer of defense fails, another layer will hopefully prevent a full security breach. Multiple systems. So the network should be easy to modify and able to adapt to network growth, because you're going to have network growth. New printers, all kinds of things. New computers will be added. Networks and IT systems require several components to operate effectively: software, hardware, data, and connectivity. Without them, the system may not operate as it should. And in case of failure, recovery strategies are needed to ensure seamless performance of a system. So recovery strategies need to be in place for maintaining your computer room environment by providing climate control and a backup power supply. Generally, if you have a large server at your business, you're going to have it in a room that's going to be about 60 degrees. You're going to need a jacket if you work in that room, because if it gets too warm, your computer components fail. And when you have a huge network and a whole bunch of servers in a room, it produces an amazing amount of heat. So you have to like super chill that room if you have a whole lot of network systems in there. because it's going to cause a failure. And a backup power supply. Yeah. Securing all network hardware, including servers, desktop, and laptop computers, wireless devices, and peripherals. Which means that door should be locked if you get into that room as well. Providing connectivity to a service provider, including fiber, cable, and wireless. Right. Because you got to make sure you're not overloading the capacity of all your connections. Keeping backup for software applications, including data interchange, email, enterprise resource management, office productivity, etc. Because if you have a certain hard drive that fails, you don't want to lose all that data. You should have backups. And it should automatically back up like every day, every night or something, automatically backs up everything. And then backing up and restoring data. Kind of goes right along with that. Downtime could be devastating for some business applications. Like I said, Amazon.com goes down, it's a huge problem. Larger companies may use external data centers to handle data processing and storage, which often runs in parallel with in-house data storage. So if the power goes out in your building, that may not be the only place that you're processing data and storage. But this is costly that many companies cannot afford to do because, yeah, you're paying a separate company or maintaining an entire separate site. So, all right, that is the bottom line. Designing a secure network can be pretty overwhelming. Firewalls, routers, and switches contribute to the security of a network, but it's not always enough. Network must be properly designed and configured to keep it running smoothly. Let's look at the assignment here. Which core network principle states a network should be easy to modify? Which states that access permissions set to an object set to none, default access. Simplifying design is not easy, but easier to understand and fix. Braid needs to upgrade the network. It takes the time to review the state and set in the pre-existing security controls. Which principle is he following? And which principle is based on the idea if one part of a system goes down, the entire system will also crash? There you go. All right, Griffin. There you go, sir. You got your assignment for the week. Have a good one.